everybody. Section 12.2, which is going to be about series. Now behind me, and I know I'm going to apologize in advance. I know I've got a little bit of a little light bulb deal that's going on here, a little reflection. So I'll try to make sure I stay under that as I go through this lesson. But you'll notice that you're given a series or a sequence here. 1, 3, 5, 7, 9, 11, 13. Now you would recognize out of that the pattern. We can see that it's just adding by 2. Now, today is going to be all about series though. So what is a series? Well, a series is just taking the terms of a sequence and adding them, maybe subtracting them depending on what they do with it. So in other words, if I'm given the sequence 1, 3, 5, 7, 9, 11, 13, the series that would match to this would be just 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13. You're adding the terms of a sequence. So a series is just an addition of the terms of a sequence. Now, in some cases, what we might see is we might see that you've got a sequence that's going here, but in the end they'll put the 3 dots. Now what that represents is that this would be an infinite sequence. In other words, this pattern would go on forever and ever and ever, all the way to the point where if you wanted to try to write out all of the terms of that sequence, you'd die writing odd numbers. We don't want that to happen. So a series can also have that, is that if this was an infinite sequence, then the series that could be tied to it would be an infinite series. And so it would have just an addition at the end, including those 3 dots. Now, in most cases, though, what you're going to be dealing with is some sort of a partial sequence or a partial sum, so to speak. Okay? So when we have an infinite series, we're going to probably be looking at a partial sum of that series. So as an example, let's say that we are given a series, or excuse me, given the sequence. Okay, so again, we're giving ourselves another sequence. 1, 2, 4, 8, 16, 32, 64. Okay, so this is a sequence that obviously has a first term and a last term. But what they're going to ask us to do on something like this is to say find S sub 5. Okay. Now what the S is going to refer to is a sum. Okay. The 5 is going to represent the first 5 terms. So when I look at my sequence, S sub 5, the series, would be the following. 1 plus 2 plus 4 plus 8 plus 16. The first, the second, the third, the fourth, and the 5th term. That's what this 5 is representing, is that you're adding the first 5 terms of the sequence. Now, the numbers here are fairly small. You should be able to handle that on your own. But if we were to add this up real quick, I think we can probably do this pretty easily mentally. Now I could work 1 plus 2 plus 4 plus 8 plus 16. I think it might be a little easier though. Let's go the other way. 16 plus 8, 24. 24 plus 4, 28. 28 plus 2 is 30. Plus the 1, we get a sum of 31. If I did it the other way, 1 plus 2 is 3. 3 plus 4 is 7. 7 plus 8 is 15. 15 plus 16 is 31. Doesn't really matter. Whatever suits your fancy in that case, do it. Okay? We will see in some following examples in upcoming sections where we might have 40 terms that we need to add. And we're not going to want to have to do it term by term by term. That's coming. Okay, that's a special kind of sequence and a special kind of series that we'll take a look at. So today it's going to be all about general series and doing some things with those. So as we move on then, we now know about partial sums. So a series can also then have a representation to it. Okay, so as an example here, let's say that we give ourselves a series of, let's go 4 plus 8 plus 12 plus 16 plus 20. All right? Now, when we look at this, we can see the series, we're just adding the terms of a sequence. So we have to keep in mind that when we take a look at the terms that are written out in a series, the 4 from the sequence would be a sub 1. 8 would be a sub 2. 12 would be a sub 3. 16, a sub 4. 20 is a sub 5. So look at this without the additions. I'm not going to erase them, but just look at it without the additions, and you'll have a sequence: 4, 8, 12, 16, and 20. Think we could write an explicit rule for the individual terms? Keep in mind we're going to do this explicit. Okay, so if we look at the explicit rule here, we should see a pattern that we are adding by 4. Okay, so let's build it. The explicit rule, if we started with a sub 2, hopefully you would agree, would be 4 plus 4. A sub 3 would be 4 plus 4 plus 4, because we're starting with 4, adding a second 4. Let me highlight something here. I'm going to highlight this 4 right here, is that this is the beginning value of 4. Term 2, add 4. Term 3, add 4. Okay? So notice that this just looks like 4 times 2 here. Okay, so again, explicit rule. 4 plus 4 times 2. If I keep that pattern going then, a sub 4 would be equal to what? 4 plus 4 times 3. All right? That should be enough for us to see the explicit pattern. Again, in an explicit rule, the term number is what's used to calculate the term value. Okay, so again, term value are the actual terms, the 12, the 16, the 20, and so forth. So let's go general rule, a sub n. Notice what doesn't change. The original 4, okay, from the beginning. Notice in every one of these, we're essentially multiplying by 4. We could look at this first one and say 4 times 1. So notice that that's not changing. But what is? Notice it's a sub 2, a 1. A sub 3 is 2. A sub 4 is 3. So if it's a sub n, this number that I'm multiplying by has to be 1 less than that, which would be the quantity n minus 1. 4, 3, n minus 1. Now, what we'll do, we'll just clean that up just like we did in the first section, 12.1. And we would get to say, with a little bit of work here, that a sub n is equal to 4 plus 4n minus 4, or we could just say 4n. 4 times 1, 4 times 2, 4 times 3, 4 times 4. This is one way to do it. If you came up with this right away, awesome. Works perfect. But what we need in order to write what we're going to call a summation, we're going to need the explicit rule for the terms of the sequence. Okay? So even though this is written as a series with all the little additions in here, we still need the explicit rule for the terms of the sequence. All right? So we have the explicit rule. So now this idea of what they're calling the summation notation is going to be a little bit of new terminology. You've probably seen it before. So I'm just going to rewrite the explicit rule here. Is that a sub n is equal to 4n. Okay, that's what we found from down there and all that work. I just got to get a little bit of space for myself here. Now, the summation, though, what they're going to do in a summation is they're going to use a capital Greek letter called sigma. And what sigma looks like is it's going to look like this big, goofy-looking E is a way that many people would describe it. Okay, that's what we call a sigma. Now, this explicit rule that we just found, we don't use the a sub n here. And a lot of times what they do is instead of using n's, they use what they call k. They just use the letter k. And I think, in all honesty, they're only doing that just to make sure that we understand that we have a series, not a sequence. Now, the letter could be anything you want. You could make it R, you can make it X. It doesn't matter. If I stuck with the N here, what we would write in this position right here is the explicit rule for the terms. So I'm going to take just that 4n, the explicit rule itself, and I'm going to put it in that position. Then what's going to happen is there are going to be two numbers that are going to be listed right here. And what those are going to be essentially are numbers that let us calculate the terms of the sequence. So what they'll do is they'll give us a starting number. Now, since we're using the letter n as the variable here in the explicit rule, down on the bottom, they're going to say n equals 1 in this case. All right? Because if I do 1 and plug that in, 1 times 4 is 4. Now, when I look at this, I have 1, 2, 3, 4, 5 terms. So what they're going to do is, since there are 5 terms, we're going to put a 5 on the top of that sigma, or on the top of the summation. So what this is telling us then is how we're going to calculate and then add the terms of the sequence. The value of n, or in a lot of cases, the letter k that they use, which there would be a k over here, are going to be integers, starting at 1 in some cases. Sometimes they will give it to you and it's not starting at 1. So they'll do some things. The editors of this book, the publishers, are going to try to throw you off a little bit on some of those. So you've got to be a little bit watchful, because this number here may not always start at 1. Okay? They're going to play with your mind a little bit, but don't let it throw you off. Okay? So what's going to happen? So this is what we call the summation notation. And so what we need to keep in mind is that in the pieces of this, now I'm just going to start listing some of the pieces of things. Hopefully this is going to be easy enough to see with the green. This is going to be the value or the number used to find the first term. Okay? Now keep in mind this will be an integer. Okay, it'll be just an integer. It's not going to go 1, 1.1, 1.2. Okay, it's going to be 1, 2, 3, 4, 5. This number up here is the last number that's going to be used to find the last term. So what's going to happen here is we start with the number 1. We're going to work our way and plug in 1, 2, 3, 4, and 5. So we plug those in. So this is what it would look like. It would look like 4 times 1, using this number, plus 4 times 2, using the next integer, plus 4 times 3, plus 4 times 4, plus 4 times 5. Okay? So notice, 4 times 1, 4. 4 times 2, 8. 4 times 5, 20. Okay? So we just need to keep in mind that we're going to be asked to do some of this adding or finding the sum of a series using a summation notation. So we have to keep in mind it's all of this right here, which is the summation notation. First integer to use, last integer to use, and go up by integers. And then the biggest thing to keep in mind is that the 4n is the explicit rule for the terms of the sequence, okay, or the explicit rule for the terms. So that's really all there is to a summation. So let's do some examples of that, and let's see where we go. All right, so here's some other examples. We're going to continue to write in summation notation here. Now again, I apologize if I get this a little bit high and into this little spot here, so I got to make sure I keep it down. So let's say we have this as our series. Ooh, that pen's died. All right, here we go. -2 plus 4 minus 6 plus 8 minus 10. Now, you might be looking at this going, wait a second, Mr. Varsht. You've got additions and subtractions. How can that be a series? Because you're not adding. Well, keep in mind, a negative is just adding a negative. So I'm still adding terms. So we just have to keep in mind that within the explicit rule, we have sign changes taking place. Okay? So if I highlight this, let me highlight the additions here. -2, positive 4. -6, positive 8. -10. Now, think of the explicit rule here. Now keep in mind that the terms, you have a sub 1 or first term, a sub 2, a sub 3, a sub 4, a sub 5. So there's some things we can get right away, even before finding that explicit rule. We have 5 terms. Now, in the explicit rule, is there a way that we can go from -2 to 4? So look at it from that rule. A sub 2 looks like -2. What's the pattern here? It looks like we're not going up. It looks like there's a multiplication by a negative number. So let's see if this makes sense. A sub 1, -2 times 1. A sub 2 is equal to negative 2 times 2, except that doesn't work, does it? This would have to be what? A negative 2, wouldn't it? What if I wrote that as negative 2 to the 0 and negative 2 to the first? That gets me the first two. But if I tried that for a sub 3, that doesn't work, does it? We got to look at a different pattern. Keep going. Now, because there's a negative here, let's maybe isolate that negative. Could we say in a sub 1 that it's negative 1 times 2? Sure. A sub 2, if we've got to get to a 4, we could say 2 times 2. Okay, that would be okay. But that negative 1 would have to be to a second power. Okay, now think about it for a second. Negative 1 to a second power is going to be positive 1. Negative 1 to a first power is negative 1. 2 times 2, second term, positive, positive 4. Let's see what happens in a sub 3. Let's take negative 1 to the third power because that's going to generate the negative. And then 2 times 3. Negative 6. Let's see if it fits. Keep going. A sub 4. Negative 1 to the fourth power. 2 times 4. Positive 8. Looks like we have something. The only thing I might want to include up here is a 1. So now take a look at your pattern. First term, using a 1, using a 1. Second term, using a 2, using a 2. 2 as an exponent, 2 as a multiplier. 3, using 3 as an exponent on the 1, 3 times the 2. 4, exponent 4, using the 4. Looks like that's fitting, isn't it? So it looks like our explicit rule a sub n would be equal to negative 1 to the power of n times 2n. Okay. So we need to keep in mind the explicit rule. All right, so again, we're just trying to write the summation here. So yeah, the bigger key on this, or the bigger challenge, is going to be doing a little review of section 2.1, the explicit rule. So in my summation notation, I'm using n here. If I were to be a little bit more consistent for what the textbook is going to do, instead of n, they're going to use k. Don't let it throw you off. Just a different letter. So we're going to start with k equals 1 to represent the first term. We've got to go to the fifth term, so the top number is 5. And then the explicit rule in behind. So negative 1 to the power of n, or excuse me, not n, but k. This has to match the value or the letter in that position, times 2. Okay, and there you have it. So you'll notice the summation portion, the sigma, the first number, and the last number is not really a big challenge. The bigger challenge is writing that explicit rule. We can always use extra practice on that. Let's make it a little more challenging. Let's say our pattern is this. -1 plus 1/4 plus 1/9 plus 1/16 plus, oops, excuse me, I'm switching signs here, minus 1/9 plus 1/16 minus 1/25 plus 1/36. Now, hopefully you're seeing the numerators really aren't changing. Those are all ones, okay? So if I start working on that rule, again, keeping in mind a term number, okay, so a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6. So again, I'm just looking for some pattern here, so I know that I've got 6 terms here. Now, the one thing you want to notice here is that you've got one that's just an integer, and then the rest are all fractions. Could I write that over 1? I'd hope so. Now, to kind of speed things up here, don't look at the negatives for a second. Just look at the terms. Look at the denominators, because we know the numerators are all ones. I can put this negative out front, so no big deal there. The numerators are all the same, okay? So I could argue, at least to start, that if I start looking at my explicit rule, I know that I could essentially say there's a 1 in that numerator. Now, we'll come back to the negative here in a moment, but look at the denominators. 1, 4, 9, 16, 25, 36. Hopefully you can see that's a pattern of perfect squares, isn't it? Perfect square of 1. Perfect square of 2. Perfect square of 3, 4, 5, and 6. So it looks like we're taking the n value, or in our case, excuse me, again, matching my letter here, the k, and we're squaring it. Okay? But now, that doesn't help us with the negatives here. Notice that the first term is negative, the third term is negative, the fifth term is negative. Odd numbers. So if I made a negative here, and I raise it to the power of k, -1 to the first power is -1. -1 to the second power would be +1. -1 to the third power, we're back to negative. Hey, we got it. Okay? So there's our explicit rule. So let's get the summation. So in the summation, right away, we can say that k is going to start at 1, my first term. It's going to go up to the 6th term. And then finally, the explicit rule. And there we have it. Now, you'll have some other ones where the explicit rule is going to be maybe a little bit more challenging than that. So keep in mind that this process is to give you the idea or the processing steps to go through it. So think about what we did. We look for the pattern. We definitely want to name our term numbers here. So we're getting the term numbers that we're looking at, whether you use n, k. I'm not going to use that. I'm not going to worry about that. Just make sure that you're consistent with it. Start at 1, end at 6. Start at 1, end at 6. But the key again, finding that explicit rule. That's going to be the big part. Now, so from this, what you're going to then transition to is actually evaluating the summation notation. So in other words, they're going to give you the summation and they want you to figure out the total, the addition of all the terms. Now, this is where you're going to see a little change on some things. So when we look at it from this perspective, they might change the beginning value you use. So let's say we do that. Let's say k is starting at 2 and goes to 5, and the explicit rule that they give is 1 over 3 to the power of k. Now, because this is starting at 2, don't let that throw you off. It's just a starting value to put into your summation. Now, don't overthink it. All you're going to be doing is putting in integer values from 2 up to 5 in here. So if I were to write this out, kind of doing this by a little bit of a color code here, okay, so I'm going to change this to a brown just so it's a different color. I'm going to change the 5 to a brown just to kind of help highlight this. So when I go to actually calculate this, okay, when I go to calculate, what my terms would look like are as follows. I'd have 1 over 3 to the second power. There's my first term, and I got to clean it up. Then I'm going to add to it 1 over 3 to the third power. Goes up by an integer. Then I'm going to add to it 1 over 3 to the fourth power. And finally, I'm going to add to it 1 over 3 to the fifth power. Now, you might be looking at that going, I got to do this? I actually got to calculate all of that? Yeah. But don't make it hard. The common thing that somebody might do with a problem like this is they might think, okay, I got to write this as 9, 27, 81, 243. So I've got to find the common denominator that goes all the way to 243. Yeah, you do, but don't make it hard. You have 2 3s here. You have 5 3s in the end, which means common denominator has to have 5 3s in every one of them. So don't overthink it. Hopefully it would make sense that if I multiply by 3 to the third over 3 to the third times 1 over 3 squared, that's going to get me my 3 to the fifth in the denominator. Let's do it in the second one. In this case, I only need 3 squared. 3 squared over 3 squared times 1 over 3 to the third. Should hopefully be seeing the pattern's not too hard here. Let's do another one. Now I'm only missing a 3. 3 over 3 times 1 over 3 to the fourth. And finally, plus 1 over 3 to the fifth. That's our common denominator. So just like that, we've got our common denominator. Now go ahead and clean some things up. So from here, let's do some mental math. We know that 3 to the third times 3 squared is 243. So what do we have? We're going to have a common denominator of 243 because it's the same here, 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 and here, 3 to the fifth. Now, let's just clean up the numerator. 3 to the third is 27. 3 squared is 9 plus 3 plus 1. Add them together. All right. I think I'm going to make it easier. 9 plus 1 is 10. 27 plus 3 is 30. 30 plus 10 is 40. And there, everybody, is our result. Now, could I have gone to a calculator to do it? Yeah. But don't avoid doing the fractions. You can't get better at them by avoiding. Okay? You got to work with them. So do that. All right. I want you to pause the video. Do this problem. Let's say that you're given this summation. Let's say you're given this summation that runs from, let's say, k equals 1 up to 6 of k squared minus 10. Okay, pause the video. Come back when you're done. Check your work. Here we go. So, as I do this, again, I know that I'm going to have 6 terms here. 6 minus 1 is 5, but I'm using the first term. Okay? So I might want to keep in mind that the number of terms, in this case, will be 6 minus 1, top number minus bottom number, plus 1. So in the grand scheme of things, the top number minus the bottom number plus 1. Okay? Now we add the 1 because you're using the first term. Okay? 1, 2, 3, 4, 5, and 6. You use the first term. So you can't just take the difference. You have to add the difference, or find the difference, and then add 1. All right, so here we go. In calculating this, if I take the time to write it out, I'm going to do 1 squared minus 10 plus 2 squared minus 10 plus 3 squared minus 10. Notice my use of parentheses here. Plus 4 squared minus 10. I'm probably going to run off the screen here. 5 squared minus 10. And finally, plus 6 squared minus 10. Now, there's lots of different ways that a person might take a look at doing this, because we could technically clean up all of the multipliers and then notice that we're subtracting 10 6 times. We can do it that way. We don't have to do it that way. I might just do the work manually. I can go either way. 1 squared minus 10, that's 1 minus 10, or negative 9. 2 squared is 4. 4 minus 10 is negative 6. 3 squared is 9. Minus 10 is negative 1. 4 squared minus 10, 16 minus 10 is 6. 5 squared minus 10, 25 minus 10. That's 15. And finally, 6 squared minus 10, 36 minus 10 is 26. Now, you might make sure to take a look at the work a little bit and see what are some things you might be able to eliminate as you go. Well, let's take a look. I see a negative 6 and a 6. No sense in subtracting it and adding it back in. It just becomes 0. From here, I think maybe I'm just going to start working. Negative 9 minus 1 is negative 10. Negative 10 plus 15 is 5. 5 plus 26, 31. Now, if you want to use a calculator, use a calculator. But keep in mind, you still need to know how to do it by hand. Okay? But don't overthink it. All right. We're just taking a look at other examples. One more of this. We're getting close here, everybody. We're getting close. I know the video is getting a little bit long. But again, go as far as you need. If you feel comfortable, move on. All right. Let's say we've got this summation. A summation that starts where k is equal to 1 and runs to 4. 2 times negative 3 to the power of k. All right? Pause the video. Come back when you're done. All right. Here we go. So if I take the time to write out my terms, which is always a good thing, make sure that I've got it all, putting in values from 1 to 4. So again, the number of terms will be 4 minus 1 plus 1. Again, top minus bottom plus 1. We have 4 terms. Okay, let's put them in. 2 times negative 3 to the first, plus 2 times negative 3 to the second, plus 2 times negative 3 to the third, plus 2 times negative 3 to the fourth. Let's clean it up. 2 times negative 3 is negative 6. Negative 3 squared is 9, plus, or multiplied by 2 is 18. 3 to the third, 27, but negative 27 times 2, negative 54. And then finally, negative 3 to the fourth is 81, times 2 is a positive 162. Yeah, I'm probably going to go to a calculator here just because those numbers are fairly large, especially when you start getting up into triple digits. Trying to add mentally isn't quite the easiest. So I'm going to go ahead and grab my calculator here. So negative 6 plus 18 minus 54 plus 162, and I get a total of 120. Okay. So again, nothing that should be really extreme or out of the ordinary for you. Nothing big. But now take a look at our last example. You might be looking at it going, wait a second. What about that one? Last example. A summation. K equals 1 to 5 of the number 7. There's nowhere to put the value of K, is there? What do you think that means? Think about it. If all you have is just a number here, each term still has to be created. We still have a number of terms, 5 minus 1 plus 1, or 5 terms. We have to have 5 terms. There's just nowhere to plug a number in. So what do you think each term is? Don't overthink it. It's not hard. Hopefully you're thinking 7. How many terms of 7 will you have? If you're given just a constant, it means that every single term is the exact same thing. 7, 7, 7, 7, 7. Total 35. So don't let that throw you off. There's a lot of people that would look at this and they're going, ha ha, they're going to start creating a hairline like mine. Don't do that. Don't overthink it. It's just a constant value. So you still need to have 5 terms. It's all just the same value. Keep that in mind. Don't let that throw you off. So you're going to have a mixture of those types of things, everybody. You've got the time to work on it then. Going into tomorrow, take your time. Make sure you know it well. See me in a Google Meet if you got any questions. Take care. Good luck. Bye-bye.